go. Alrighty. Good morning, ladies and gentlemen. Happy Tuesday morning. This is April 28th. This is Algebra 2 CP. While I go through the couple reminders that I usually do at the beginning of every class, I do have a little quick do now for you, as you can see on the screen here. If you could try to factor each of the following expressions, shouldn't be very tricky. We should be very used to factoring at this point. We've done a lot of it in all of the problems we've really done throughout the year, but factoring will come back in a big way today. So if you could go ahead and try to factor those down while I just talk about the little couple quick items I have to, then that would be really appreciated. So make sure if you haven't done so already that your microphone is muted and your webcam is off. I think everybody's gotten used to that. Make sure if you haven't done so already just to fill out that quick attendance form on Google Classroom. It's the same one. And lastly, regarding your progress assessment, I really appreciate everybody that submitted the progress assessment on time, which is fantastic. I really don't think that deadline of Sunday night was unreasonable, and it seemed like you guys were able to step up to the plate for the most part. That progress assessment is in your email, so please make sure if you haven't done, or if you didn't do it, if it totally like you just forgot, please reach out to me. I cannot allow you to do the same version of the progress assessment because the answer key is now out there on Google Classroom. But reach out to me and say, hey, Mr. Giorgio, I just forgot to do the progress assessment. What can I do? And I do have another version that I can send you that you can complete still for credit, okay? Do not get used to that as being a routine. That is just a one-time thing as we now get used to this sort of weekly structure and weekly routine in Algebra 2 CP. I don't want to keep having to lag behind because of not meeting deadlines. I don't think that's that's reasonable. Like, I think it's definitely plenty of time from Thursday afternoon all the way to Sunday night is definitely a long stretch of time to be able to do some problems that should take about a half hour. So, yeah, please reach out to me, though, if for whatever reason you just forgot, you slipped your mind, you forgot to do the progress assessment, you forgot to turn it in, just let me know. All right. I will have those grades in Aspen today. I'm going to probably do them during our lunch hour so I can have them prepared for you. I was planning on having them ready for the start of class today. I did post the answer key for the start of class today, so you should look that over. But if after looking over the answer key and then looking at your grade, you still have a more specific question where you're like, hey, why did I get that? Or, hey, could you explain this problem in a little more detail? I'd be happy to do that during my office hours with you. All right. I do have, I'm meeting with a student today after school, but if you want to meet, just send me a message, let me know, we'll schedule a time. All right. So, with that all being said, let's now get into a little bit of factoring. You might be like, well, how is this idea of factoring going to tie in to our graphing rational functions? And to that I say, you'll see. All right. So let's go ahead and start factoring. We should be able to do all of these with little to no trouble at this point in Algebra 2 CP. If I'm trying to break down these trinomials into two binomials, here, here, and here, I just wanted to give you this as a little refresher. In order to break down x squared minus 2x minus 8, I need x and x. I need different signs, one negative, one positive, because we're multiplying to a negative number, so the signs need to be different. And what combination of factors for 8 is going to result in getting this negative 2 in the middle? It's going to be a minus 4 and a plus 2, just like that. And so that's how you would factor down x squared minus 2x minus 8. Next one, very quickly, same deal. We need x and x. Everything's positive, so it makes sense to keep all of my factors positive. And then what combination of factors of 12 is going to combine when we distribute to get 13x? That's going to be 12 and 1. Right? So it would factor down to x plus 12 and x plus 1. And last but most certainly not least, we have x squared minus 11x plus 30. I need x and I need x. My signs need to be the same because we're multiplying to a positive number at the very end. But since we're adding to this negative quantity in the middle, it makes sense that both of my signs should be negative, and then the combination of factors that works is 5 and 6. Okay, or 6 and 5. You could write them obviously in either order. Any questions as to how I came up with that? Just quick factoring. Definitely shouldn't be a area of struggling right now. Shouldn't be a troublesome spot at this time. But if it is, now's your chance to ask. Speak now or forever hold your peace. Factoring, making sense. We're happy. Okay, because guess what? Factoring is now going to come back in a major way to interact with the rational functions that we've been doing so far. Consider a problem like this. If I asked you to sketch a graph, of this. X plus 1 divided by x squared minus 3x minus 4. Oh boy. Oh boy. That's definitely a rational function because there's x's in the denominator, but we've yet to see one of that complexity, particularly where we have x squared in it. And also that just looks, it should just look a lot harder than what we've done before. But, hopefully your Algebra 2 instincts are kicking in a little bit. Seeing an expression that looks like this in any part of any problem, just like these trinomials up here, before we actually dive into this, it's much to your benefit to factor, right? Let's try to simplify it down first and see if we can mess around with it a little bit to simplify. It's just like, I compare it a lot to those square root problems where they look really ugly, but then you pull out that greatest common factor and it simplifies nicely. A similar thing is going to happen here. I can break this down now to be, instead of writing it as a trinomial in the denominator, let's factor this. Maybe that'll provide a little more clarity as to what's going on. Because, yeah, how would you even go about finding the vertical asymptote? If I said, hey, what's the vertical asymptote of that? What number, if I plug it in for x, results in dividing by 0? You'd be like, I don't know. So it's much clearer and easier to actually find that value if you do some factoring. This is going to factor down to be, let's see, we need x and x. We need one positive, one negative, and it looks like the factors of -4 that are going to combine to -3, we need -4 and +1. Okay? Everybody hopefully sees how that factored down. Now, if you look at that, you might be like, ooh, wait a minute, x plus 1 in the numerator, x plus 1 in the denominator, wouldn't those factors cancel out? And the answer to that is absolutely they would. X plus 1 in the numerator, x plus 1 in the denominator go away, and now we're left with a much simpler function to graph of 1 over x minus 4. The reason why there's a 1 in the numerator is because once you cancel out everything, there's still this factor of 1 out here. It's 1 times x plus 1, so that's why that 1 stays floating in the numerator. It wouldn't make sense to put 0 in the numerator because 0 divided by anything is just 0, and you still clearly have stuff in the denominator, so you need to write this factor of 1 up there. It's just like any number divided by itself is equal to 1. That's why you have a 1 over x minus 4. Okay? And now that function is much, much easier to graph. If I want to handle this, I can say, well, what's my vertical asymptote? My vertical asymptote is x equals 4 because 4 minus 4 result in dividing by 0. What's my end behavior asymptote? Well, the degree of the denominator is larger. It's degree 1 versus degree 0. So your end behavior asymptote is 0 plus any vertical shift, but there is no vertical shift. So I would now go ahead and sketch a graph of this. Let's see. Let's do my best graph over here. Something kind of like this. I have my vertical asymptote at 1, 2, 3, 4. I have my end behavior asymptote at 0. That's just the x-axis, right? Now I can go ahead and test some points just like before. No problems here. Should be all familiar territory. Right? Which points am I going to pick? I'm going to pick 2 to the left and 2 to the right of that vertical asymptote. So my vertical asymptote's at 4, so let's pick 2 and 3, as well as 5 and 6. That just skips over that vertical asymptote position of x equals 4. If I take 2 and plug it in, let's see what we get. 2 minus 4 is -2. 1 divided by -2 is -1/2. 3 goes in. 3 minus 4 is -1. 1 divided by -1 is -1. So I have 2 comma -1/2. 3 comma -1 right there. 5 goes in. 5 minus 4 is 1, and 1 divided by 1 is 1. And lastly, 6 goes in. 6 minus 4 is 2. 1 divided by 2 is 1/2. And so I get a graph that looks kind of like that. Yes, you could probably picture, without me even drawing in those curves, what they actually look like. All right? Does everybody see that? Just to provide you with an even clearer picture, what I did for you, brace yourselves. We're about to get fancy schmancy here. Brace yourselves. I actually came up with a little image on Desmos for you to show you what's going to happen. We're going to switch over to my AP Computer Science layout. This is not, you guys are not AP Computer Science. Don't worry, we're not going to suddenly start doing coding. But bam! Look at that. Check that out. Little Desmos graph of what's going on here. Here's our function of x plus 1 over x squared minus 3x minus 4. Oh yeah, we're getting fancy. We're getting fancy. However, there's one thing I want you to notice about this function, right? Notice that it does approach, just like you would expect, this function approaches the asymptote, approaches the asymptote, approaches the asymptote, but will never actually touch it. Same thing down here. It approaches, approaches, approaches the asymptote, but will never touch it. That's exactly what happens on this side as well. Approaches the asymptote, never touches it. Here we approach the asymptote, approach the asymptote, approach the asymptote, but never touch it, right? Nothing crazy going on here. However, there actually is something crazy going on here. If you notice, I can slide this point over anything and it shows the corresponding x and y value. Not surprising that none of the other x values give us an issue. But there is some weirdness that happens right here. Oh, I can't get it. There it is right there. Yikes. Yikes. We have an undefined point in the graph at x equals -1. What's the deal with that? I just moved my mouse off of it. But what's the deal with that? If you notice, I specified my vertical asymptote. I specified my end behavior asymptote. We graphed it just like normal. We haven't dealt with any undefined. It's hard to make that stay there. It's like my mouse. I got to just keep my finger pressed down. We haven't dealt with any undefined points in any of the other graphs that we've taken a look at so far this year. Come on, stay on the point. There we go. Maybe I got to zoom in a little bit. It might be a little easier. There we go. So what's going on? Well, why is there an undefined point at -1 specifically? Why at -1 specifically? Well, the reason why there's an undefined point at -1 specifically, not like 1 or 2 or 3 or anywhere else, why is it specifically at -1? The reason for that is because, going back to our work over here, oh, look at that transition back and forth. The reason for that is because we canceled out this factor of x plus 1. In our original problem, right, notice that I was able to factor this expression down to this expression. If I plugged in -1 for x, right, -1 plus 1 would be 0. And therefore, I would be dividing by 0 if I plugged in -1 into my original problem, because 0 times whatever that would be is still 0. And so that would be a problem, right? I'd be dividing by 0 in whatever I plugged in. Now, you might be like, well, didn't you cancel it out and just get down to this function, which doesn't have -1 being a problem? That is what we did. However, that comes at a cost. This cancellation comes at a cost. And it comes at a cost of a singular undefined point existing at x equals -1. Because -1 would have still been a problematic value to plug into the denominator. What happens here when we cross out and cross out is we are essentially saying the graph of this function is equivalent to, it is the same as the graph of this function, with the exception of one point. And that one point in this particular case occurs at x equals -1 because hey, I clicked it right away, because -1 plus 1 would result in dividing by 0. And that one singular undefined point is what's referred to as a hole. Okay? And I would say here that there is a hole at, that's our little at symbol, x equals -1. Okay? So, just to define it for you quickly, a hole in a graph is a singular undefined point on a graph caused by canceling, two L's, canceling out a matching factor from the numerator and denominator. Okay, so a hole is a singular undefined point on a graph, which is caused by canceling out a matching factor from the numerator and denominator, I should say, of a rational function. Sorry, of a rational function. Okay. What that means is, since I crossed out this factor of x plus 1, there is a hole at x equals -1. What that means is wherever your curve happens to cross this threshold of x coordinate -1, this is the threshold of x coordinate -1, correct? Wherever your graph happens to cross this threshold of -1, you're just going to put an open circle to signify that there is a singular undefined point there. And that's very important because if you graph this and then try to plug in -1, you're not going to be able to do it. So you want to make sure you indicate that that's the case on your graph. So what that's going to look like is I'm going to draw my curves as normal, approaching but not touching the asymptotes, approaching but not touching the asymptotes. But wherever my curve happens to cross this threshold of -1, which is right here, I'm going to put an open circle. Just like that. To indicate that there is, as you just saw on Desmos, there is a singular undefined point at -1. All right? Hopefully that makes sense to everybody, yes? Oh, get out of there. Okay, does anybody have a question about that at all? I know that was a lot of information. Does anybody have a question about that? We're going to do a couple more examples. Questions? No questions? Feeling good about that? Makes sense? Why the hole is at -1 specifically? Because of the cancellation there. I think that's a really important idea. All right, let's take a look at a couple more examples. All right. Oh, and by the way, when we start talking about rational functions that contain holes, we are not going to be focused on the domain and the range of those graphs, just because the domain and range gets a little complicated. Actually, the domain is something that you could definitely do. Going from left to right, the graph features all real numbers except the vertical asymptote and except the hole. So your domain would actually be -infinity to -1, union -1 to 4, union 4 to infinity. It's almost like 3 pieces now. That's you wouldn't have to worry about that on any sort of assessment, but the domain is definitely something you can do. The range is definitely a lot harder because you'd have to plug in this value of -1 into here to see what it actually evaluates to, and that gets to be a lot more complicated, so you wouldn't have to worry about doing domain and range on any rational functions that have holes in the graph. Okay, any of the regular ones that don't have holes, absolutely. Any of these that have holes, it gets a little complicated. Certainly, you can do it. It is not above your level of intellect, but definitely not something I'm going to hold you accountable for any sort of assessment. All right. Last note I want to mention before I get into a couple additional examples is the fact that, yes, it is possible, not for our purposes in Algebra 2 CP, but in general, yes, it is possible that you could factor in the denominator and not have anything cancel out. If that happens, then this graph would actually feature multiple vertical asymptotes. It would feature 2. And when you have 2 vertical asymptotes, you then have to tackle all 3 sections of the graph that are created separately. Okay? Again, that is beyond the scope of Algebra 2 CP. Algebra 2 Honors definitely does that. But just know that in the wide world of mathematics, it is certainly possible that you could have multiple vertical asymptotes if you have multiple factors that don't cancel out in the denominator. Alrighty? Okay. That being said, I think that's important to mention. But that being said, let's go through a couple more examples now and see how we can identify these rational functions with holes in them. Okay? Here we go. Let's go ahead and try this one. How about a graph like 2x plus 6 divided by x squared minus 2x minus 15. Okay, let's see if we can go ahead and tackle a graph like that. Well, one thing you might notice right away is there's a lot of simplifying that we can do, both in the numerator this time and in the denominator. In the numerator, there's not the traditional binomial factoring, but there definitely is a greatest common factor that we can take out in the numerator. And specifically, we can take out a greatest common factor of 2. And if we take out a greatest common factor of 2, you might notice the numerator will look like 2 times x plus 3. Okay? Always worth it to simplify if you can simplify. Going into the denominator now, or by the way, I should mention, always worth it to simplify if you notice that there's probably going to be a hole. Like you notice this x squared start to show up, and you notice that, oh, I'm probably going to be doing some sort of factoring, then that's when it's worth it to simplify to see if you can cancel some terms. If it's just a regular problem like what we've been doing before, like this, it's probably not necessary to take problems like that, those are from before, and simplify them. There's really not much simplifying that you can do anyway. But if you start to see x squared show up, where we're going to be factoring a lot, doing some GCFs, absolutely it's worth your while to consider any simplification options. Speaking of simplification options, we can go ahead and factor now in the denominator. I have x and x to make x squared. We need different signs to multiply to a negative number at the end. And what combination of factors is going to work to get negative 2 in the middle? It's going to be positive 3 and negative 5. And as soon as we write what I would do in classes, I would probably stare at that a little bit, and then I'd do my, whoa, do you see what's going on here? Do you notice that matching factor, x plus 3 in the numerator, x plus 3 in the denominator, we can cancel those out. Goodbye. This now goes down to simplify to 2 over x minus 5. That's just 2 over x minus 5. However, we have to remember that crossing out, that cancellation, does not happen for free. That does come at a cost. And the cost is that it creates a hole in the graph at x equals negative 3. Specifically, why negative 3? It's negative 3 because negative 3 plus 3 would have caused the divide by 0 case if we just left the function like this. What we did is we essentially said, well, this function can be represented by this function, which is way easier for us to deal with the exception of this one point that we need to account for in my image of the function. Okie dokie. So now that we have this is way easier to deal with. Hopefully this won't even take much time at all to go through a function like this. Sorry for my little cross up there. All right, your vertical asymptote here would be x equals 5 because 5 minus 5 would result in dividing by 0. Your end behavior asymptote, you compare the degree of the numerator in the denominator. Degree of the denominator is larger, so our end behavior asymptote would be 0. Y equals 0 again, just like the previous one. Okay? I'm going to go ahead and sketch my graph to the best of my ability here. Okay. I have my vertical asymptote at 5. 5 right here. Okay. I have my end behavior asymptote still sitting at 0. That's still on my x-axis. Flip that. Let's test some points now. The points specifically that I'd like to test are, since my vertical asymptote is at 5, let's pick 3 and 4. Let's also pick 6 and 7, just to see what those look like. 3 goes into my function. By the way, when you plug in, since we said that the graph of this is equivalent to the graph of this, we don't have to take 3 and plug it into the big complicated one. We could just plug it into the simpler version. You certainly could, if you wanted to, for whatever reason, take this and plug it into the top one, and you'll get the same answer, but it's way easier for our purposes to just take this and plug it into here. Okay, so just keep that in mind. Once you simplify, you can use the simplified version of the function to plug into. 3 goes in. 3 minus 5 is negative 2. 2 divided by negative 2 is negative 1. So I have a point at 3 comma negative 1. It's right here. 4 goes in. 4 minus 5 is negative 1. 2 divided by negative 1 is negative 2. 4 comma negative 2. 6 goes in. 6 minus 5 is 1. 2 divided by 1 is 2. Right about there. And 7 goes in. 7 minus 5 is 2, and 2 over 2 is positive 1. Pretty easy plug-in, right? Now, when I draw my curves, this curve is going to be the same as we've seen before. No changes there. Approaching but not touching the asymptotes. This curve, however, we have to keep in mind that we have this hole at x equals negative 3. So wherever this curve happens to cross the threshold of negative 3, it'll be right about there, I need to put an open circle. All right, so let's draw our curve. Approaching but not touching the asymptote. Approaching but not touching the asymptote. But now wherever I cross this threshold of negative 3, I need to indicate that open circle, just like that. Okay? Because there would be an undefined point, a hole, at x equals negative 3. And that would now be an accurate picture of the graph. You may be asking, Mr. Giorgio, if we don't put a hole in the graph, does that mean the problem's wrong? What does that mean as far as an assessment is concerned? It doesn't mean the whole problem is wrong, because there's a lot more to the problem than just that. However, that is a big emphasis of doing problems like this, is that you can identify and indicate on a graph what the hole is. So I wouldn't say it's not like the whole thing's completely wrong, but it is kind of missing the main point. No pun intended, because a hole is an undefined point. Jeez, that was so lame. All right, anyway, so no questions on that, yes? I want to make sure that I clear up a couple misconceptions about the holes in a graph, and if you do have a question, please feel free to just interrupt me. Just clearing up a couple misconceptions here. One thing is that when you draw the hole on the graph, it's just wherever the graph happens to cross the threshold of x equals -3. X equals -3 is this vertical line right here going through the x coordinate of -3. Wherever your graph happens to cross that. It doesn't mean, so say for example, I'll show you quick down here, just rough sketch, right? If I have a hole at x equals -3, right? Here's -3 on the x-axis. It doesn't mean on the x-axis I'm going to go ahead and draw a hole. It may just happen to land on the x-axis, but that's probably pretty unlikely. What it means is wherever your curve happens to cross this plane or this line, that's where you're going to go ahead and draw the hole. So say our graph is like way down here, where I draw my function and it goes like this, right? This is where I'm going to put the open circle. That's where I'm going to put the hole, because that's where it crossed this threshold of x equals -3. That's where the point -3 comma something would be on the graph. Does that make sense? So a common misconception that I see all the time is a lot of students say, oh, a hole at x equals -3, and they go to the x-axis and they go like that. Okay? That doesn't match up with the graph. It just means wherever on your curve it happens to cross -3, that's where we put an open circle. It doesn't mean it's going to intersect with the x-axis. It doesn't mean your curve is going to suddenly jump way up there to the x-axis. It just means in its natural shape, wherever it happens to go through there, we put an open circle. I know I'm spending a long time to explain that, but I just want to make sure that that's super clear, because that's a common mistake that I see all the time. All right. The last thing I want to point out about holes in a graph is it is possible that a hole could exist on one of the points that I plug in. For example, it is possible that on this graph, we could have had, if the numbers were different up here, a hole at x equals 4, for example. And you might be like, well, wait a minute, 4 is one of the values that I have to plug in. So how could we plug it in and then also have it be undefined? That's a great question. Well, the reason that can still work out is because we're taking this value of 4 and plugging it into my simplified version, which doesn't have 4 being a problem, versus my original version. So all that you're going to do, if you notice that, hey, we also have a hole at this same value, you're just going to take that value, and you could, if you're using pencil, you could just erase it and fill it in with an open circle, okay? Instead of a closed circle like you see there. Okay, so if it can happen, and it may happen on the practice problems that I give you, that you see that a hole exists, just so happens to exist on one of the points that we actually have to plug in, you would just create an open circle at that specific value. Okay, but you could still plug into the simplified version, because that got rid of all the divide by zero weirdness. All right, hopefully no questions, comments, or concerns on that. If you do, I'll give a little bit of time for you to ask them now. Seems like we're a-okay. I would love to keep going with rational functions, but I do want to respect your time, of course. We are out of time. Time flies when you're having fun in Algebra 2. One thing I want to remind you is that I am going to post some practice problems today on Google Classroom along with the solutions. Those will probably go up later in the day, maybe around sometime in the afternoon, maybe around 2 o'clock or so. I want to get those up there. And so you have access to them, and so you can work on them for the start of next class. It is not going to be a graded assignment, but please, it is to your benefit to give them a shot. See if you can graph those functions. The solutions will be provided, so you can go ahead and cross-check your work with the actual answer key. All right. Again, I want to remind you that your grades should be in Aspen very shortly, definitely by the end of the day. I plan on doing them during lunch, so they should be uploaded very soon. But other than that, I appreciate your attention and focus today. We will have another progress assessment at the end of the week, so just be mindful of that. Other than that, have a fantastic rest of your, what's today? Tuesday, and I will see you on Thursday. Thank you so much for your attention, and have a great rest of your day.